This video covers the Physics and Math Tutor Static Electricity 1 questions. Question 1. A student rubs an acetate rod with a cloth. Figure 1 shows the charges of the acetate rod and cloth before and after rubbing. Explain how rubbing an acetate rod with a cloth causes the rod and the cloth to become charged. So when we're looking at static electricity questions, sometimes they'll give you they'll give you a diagram to show you what's happened to the charges, and we can see initially that the acetate rod has lots of electrons inside it. So we can see, for example, 1, 2, 3, 4, 5 electrons. And then when we look in the acetate rod after, we can see we've only got 2 electrons. And in terms of positive charges, we've got 1, 2, 3, 4, 5, and we've got 1, 2, 3, 4, 5. So in terms of what's happened is that the electrons have been lost in the acetate rod, and these electrons haven't just disappeared, they have actually moved across into the cloth. So the electrons have been transferred across, and this is the idea about static electricity and about how electrons can move across when two objects are rubbed together. So by rubbing an object together, this generates friction. So friction generated from rubbing the cloth and rod causes electrons to move from the rod to the cloth. Now, hopefully you'll remember in chemistry, when electrons move, that results in the overall charge of the object changing. So this results in the charge, or the net charge, so you could put net or overall charge here, of the rod is now going to be positive because it's lost electrons, so it's lost negative charge. And the overall charge of the electrons is going to not of the electrons, of the cloth is going to be negative. I apologize, quite slow on the board. So it's neg. And that will give you easily 4 marks here. So you've made roughly 4 points. Friction has generated friction. It's caused essentially the act that we're doing, and that act causes friction. So it causes electrons to move from the rod to the cloth, and therefore the charge of the rod has changed. That gives you the answer to question 1. Question 2, after charging them, the student moves the acetate rod and the cloth closer together. Which statement is true? There is no force between the acetate rod and the cloth. There is a force of attraction and there is a force of repulsion. So what happens is that we now have overall what we've said here, and because this is a lost electrons, this now has an overall positive charge. So even though there are some electrons here, generally there is, you can see here, if you even count the number of positive charges to negative charges, you've got an overall positive charge. And here you've got 4 more electrons than you have protons, or positive charges. So this is an overall negative. And you should know that positive and negative charges attract. So your answer to this one is there is a force of attraction between the rod and the cloth. And the reason why is that opposite attract each other, and that's acceptable for the second mark. So again, if you tick the box, you must give a reason for it. You can't just tick and the marks are together essentially. So if you tick the wrong one, you lose all the marks. If you just tick it, it's just a guess. If you don't provide a correct reason, you also lose the marks. Question part C, figure 2 shows a Van de Graaff generator which is used to generate static electricity. The longer the Van de Graaff generator is switched on, the more charge is stored in the metal dome. Use an answer to complete the sentence below. The amount of charge in the metal dome is increased, which causes a potential difference between the metal dome and the Earth's sphere too. So when we look at potential difference, essentially, when we think about charge, the more charge you store, the bigger the potential difference is. So in the metal dome, you're going to have more charge, so it could be negative charges, I suppose, or positive charges, but you can have, let's say, negative charges, so for example, storing electrons, more and more electrons, this becomes more and more positively charged, there's more charge, and when there is more charge, which is Q, is proportional to voltage, which means that if charge increases, the voltage increases, because if you were to let all these electrons go across to the Earth's sphere, or if you compare the number of charges in the metal dome to the Earth's sphere, which will have no charges, there is a big difference in that. So if you were to let all the charges go across, there'll be a lot of there's a big potential difference between it. Essentially, one side's got lots of charges, the other side doesn't have any charges. So in here, the potential difference between the metal dome and the Earth's sphere, when we add more charge, it increases. So again, you can just think of this as charge increases, potential difference increases. Part D, when a potential difference between the Van de Graaff generator and the Earth's sphere is 60 kilovolts, a spark jumps between the metal dome and the Earth's sphere. The spark transfers 0.000025 coulombs of charge to the Earth's sphere. And there's the equation here, energy transferred is charge times potential difference. So this one, nice easy question. Just be careful of the zeros. So you should put 1, 2, 3, 4 zeros. So 0.0000, so 4 zeros, 0.025, so that's the charge. Then we times it by the potential difference. This is 60 kilovolts, so it's 60 times 10 to the 3. Plugging that into your calculator, you should get an answer of 1.5, and this gives you the energy transferred. So again, 2 easy marks here to collect. Question 2, we have a student did an experiment with 2 strips of polythene. She held the strips together at one end. She rubbed one down with down one strip with a dry cloth, then she rubbed down the other strip with a dry cloth. Still holding the 2 ends together, she held the strips up. What movement would you expect to see? So again, they're the same material. So if she rubs a dry cloth in it, the dry cloth electrons are going to jump from electrons are going to jump across from the cloth. So you're going to have here, and then that's connected to here. So she would down the end of the dry cloth, and then the other end. So you would expect, so here, if you rub the dry cloth on the same material, the same thing is going to happen on both sheets. So therefore, the movement you would expect to see is that they move apart from each other, because both of them are going to have the same one. So you'll have the cloth. You'll rub the cloth on this one, she'll down, then she'll down the other sheet, and therefore, what will happen is that the cloth will transfer electrons. It's probably got an excess of electrons to the polythene, and therefore it will transfer over here, and then it will transfer those electrons to here. So electrons go across, so this now becomes negative charge, and then they repel each other. Why do the strips move in this way? Because they have the same charge. And again, it's 2 marks, so you've got to say that the like charges repel. So please watch out, when if there's 2 marks, you need to give 2 points. Even though they're quite similar, you just need to say that they're both the same charge, therefore the like charges repel. Complete the 4 spaces in the diagram. Each strip has a negative charge. The cloth, so if each strip is left with a negative charge, the cloth has to be left with a positive charge. This is because particles chord, and this is electrons, so the electrons is what transfer across, and they transferred from the cloth to the strip because the strip has now become negatively charged. Now for this question, you don't actually, probably unlikely to know, and you're not expected to know which way the electrons have gone. I need this because of prior knowledge of the question at the main part, but at this stage in AI and AII, you're just expected to know that if you rub this material at the same on, if you do the same action on two parts of the same material, then if you bring them closer together, they're going to repel because they're doing the same thing on it. So that's how it works. Here it tells you specifically that each strip has a negative charge, so therefore then you know that the electrons are being transferred from the cloth to the polythene. Part C, the student tried using 2 strips of aluminium. The strips did not move. The materials such as aluminium, which electricity will pass through easily. So this one, even though it looks set up to a quite complicated question and an explanation question, is actually just a 1-mark question. You didn't really need the first part. You should know that metals such as aluminium are conductors of electricity, and polythene will not pass electricity will not pass through easily, and these are called insulators. Question 3, you wash and dry your hair, then comb it with a plastic comb. As you move the comb away from your head, some hairs are attracted to the comb. What has happened to the comb to make it attract the hairs? So the comb has become electrically charged. And how it's done that, I mean, it's only 1 mark, so that should be enough. But how it's done that in terms of the physics, electrons have transferred or moved from the hair to the comb. If the comb is now held above some small piece of dry tissue paper, which is likely to happen, so it's likely that the comb will attract the tissue paper. So things like dry paper or cloths, etc., they are likely to be charged objects or slightly charged objects. So therefore, if you bring another charged object towards it, then they are likely to be most likely they're oppositely charged. They can be oppositely charged, so most likely it will attract here. And if you rub your hands all over the comb, it will no longer attract your hair. The reason why is that the charges, because if you rub your hands all over the comb, it no longer attracts it. So if you think about it, your hands, they've got no charge or very little charge, and you've got your comb, and we'll just do it as a square object. Your cone has lots of charges. So if your hand doesn't have any charge, your charge will go, oh, I want to fill that space across, and will transfer across to your hand. But obviously what happens is that you're grounded, you're earthed, so the charges have gone to the body, which it acts as the earth. In terms of that, all the electricity will go through, and it will not result, essentially, it doesn't result into any conduct, it just travels to the earth, and just, yeah, that's the end of that charge in terms of it will just flow away from the cone and into the ground, essentially, which means that it just it doesn't disappear, the charges just go into the ground, but from the cone situation it will unlikely see those charges again. And again, it comes back to, if you've done electricity in the home, you'll know that you have like an earth wire. The electrons will flow into if there's a problem with the plug, then the electrons and the current will flow into the earth wire rather than flowing into the other parts of the plug and making it alive. Okay, question 4. A student with a nylon cone on the sleeve of his jumper. Use the words to complete it. So the cone becomes negatively charged because electrons move from the students, and it's going to move because it's rubbing it on his jumper, it's going to move it from the student's jumper to the cloth. What type of charge is left on the jumper? So if, again, we'll just use part of the jumper here, there's going to be, or we'll just do negative charges. So the jumper will have negative and positive charges. So if electrons leave the cone, then we are just left with predominant. You still might some have odd electrons there, but you'll have most likely predominantly positive charges, and therefore the jumper is now positively charged. The negatively charged comb is placed next to a charged plastic ruler. The comb and the ruler attract each other. Complete the following sentences. So if they attract each other, then they must be of opposite charge. So if the comb is negatively charged, then the ruler must be positively charged because they're opposite charges. So opposite charges attract. Electrostatic damage can damage computer chips. People working with computer chips may wear a special bracelet with a wire joining the bracelet to earth, acting as an earth wire. Any negative charge on a person will flow through the wire to earth. Which material should the bracelet be made from? So here, the bracelet wants to conduct any electricity away from the computer chip. So therefore, it makes sense that the bracelet itself can conduct electricity, because otherwise, if it was made up of a non-conducting one, then the electrons would never be interested in it. It would just continue flowing to the computer chip. So the bracelet itself wants to be made of a conducting material, and the only conducting material here is copper. And the reason you can give is that copper is a conductor, or an electrical conductor, or is the best conductor. If it was made of plastic or rubber, it would be useless because the electrons will never flow there, and then will never flow through the earth wire. They will just continue flowing to the computer chip and then damage it. Which one of the following words is described to have the rate of flow of charge through a wire? Well, the rate of flow of charge in a wire is just a current. That's a definition of the current. It's not the resistance, because that just prevents the flow of charge, and the voltage is to do with the energy or the potential difference between 2 points. So it's neither of these answers. It's a definition of the current. Question 5. The diagram shows how static electricity is used to paint a metal car panel. All the paint drops have the same type of charge. This makes the paint droplets. So if they've got the same charge, so positive and positive, or negative and negative, will repel each other, and therefore we can use the paint. This makes the paint droplets themselves repel because they're all the same charge, and they spread out. The car panel and the paint droplets have so for the car panel to attract the positive charge drops, it's got to be the opposite charge. So it's got to be a negative charge, because the positive charge will go, oh, want to go there, so we'll jump across from, or we'll go towards the negative one. It's attracted to it. So therefore, the car panel and the paint droplets have the opposite type of charge. So this causes the car panel to attract the paint droplets. And yeah, essentially we've used it. So attract, repel, and opposite, and same is not used in this one. Okay, in which of the following situations is static electricity dangerous and not useful? So in this case here, using a photocopier, that's a common use for static electricity. Very similar in terms of positive paint droplets, except this time it will be positive ink droplets onto a charged piece of paper. So therefore photocopier is fine. A smoke precipitator will use static electricity as well. But the dangerous one, the key one is dangerous and not useful, is going to be refueling an aircraft, and that's by far and away the most dangerous one out of these three. The reason why is that sparks can cause explosions, they can ignite fuel because you're giving it a sudden energy one, makes it flammable, and then cause a very quick explosion. And sparks can be generated from static electricity, and a spark is just generally a very quick, like a load of electrons moving very quickly, so a very high potential difference which can generate a spark. Question 6. A student uses same everyday items to investigate static electricity. A strip of plastic is cut from a plastic carrier bag. This plastic strip is rubbed with a cloth, and the plastic strip is hung over a wooden rod. The rubbing the plastic strip with a cloth causes the strip to become negatively charged. So this is caused because the electrons, so again, a cloth and the plastic strip, if it's to become negatively charged, it's got to gain the electrons. So this becomes negative, and the cloth becomes positive. So this is an electron, and the cloth is left with a positive charge because it's lost electrons. So if it loses electrons, then the remaining charged particles will be a net positive charge. Again, very similar to chemistry. When the plastic strip is hung over the wooden rod, the two halves of the strip move equally away from each other. What two conclusions would the student make about the forces acting on the two halves of the plastic strip? So if they're moving away from each other, so first of all, if they're moving away from each other, then the forces are in the opposite direction because they're going in the opposite way. So therefore the forces must act in the opposite direction. And the other key thing here is equally away from each other. So if they're equally away from each other, that means that the force must be the same on both strips. Otherwise, if one force was greater, one would move away faster than the other. So if they move away the same, then therefore they must be the same force acting on each other. For part B, electrical charges move easily through some materials than other materials. Which of the following materials would an electric charge move most easily? So this one is just aluminium because that's a metal. Glass and rubber. Glasses does not allow electrons to flow, and rubber also does not allow electrons to flow. They're both insulators. Aluminium is a conductor. Question 7. A student takes off a nylon fleece and feels a small electric shock. He realizes this has happened because his fleece has become charged. Explain why the fleece has become charged. So again, think most of you would have probably taken a fleece off and rubbed it again and understand the process in terms of that the fleece will rub against a shirt. So that's the first thing, and you can put that as the first point here. So the fleece will rub against the shirt. So the fleece rubs against a shirt. This generates friction. Again, I'm going a bit beyond, it's only 2 marks, but I'll just explain in the physics as well. So this generates friction between the shirt and the fleece. So very similar to the previous situations we've done involving rods and cloths. This is the same idea. So the fleece rubs against the shirt. This generates friction between the shirt and the fleece, and this causes electron transfer. Now again, it's not clear which way the electrons are transferred because it only says that the fleece becomes charged. It doesn't say it becomes negatively charged or positively charged. Therefore, you're not sure in this case which direction the electrons are going, but you need to mention that there is an electron transfer. Question 7b, only 2 of the following statements are correct. Positively charged objects repel negatively charged objects. So hopefully we know this, that this is going to be incorrect because positive and negative attract each other, so we know that this is wrong. Electrical charges move easily through metals is correct because metals are conductors. They have metallic bonds which allow electrons to flow through. Static electricity is safe, it never causes any danger. One of the earlier questions proved that it does cause danger. So by process of elimination, electrical current is the flow of electrical charge, but this is the definition of electrical current, so hopefully you should know this from your early electricity studies. So current is just a flow of charge. Part C, we have the diagram shows a lightning conductor attached to the side of a tall building. If the building is struck by lightning, charge flows to the earth through the lightning conductor, which is the materials in the list is used to make the lightning conductor. Again, we want it's a lightning conductor, so we need that material to be a conductor. So we're going to say copper, because copper is a metal and is a good electrical conductor. Again, glass and plastic are not very good conductors of electricity, they are insulators. Complete the sentence by drawing a ring around the conductor. The resistance of the lightning conductor is something the resistance of the building. Well, the conductor must be less because, again, electricity, electrons flow through the path of least resistance. So the lightning conductor, if it's going to be, if you want electrons to flow through it, you obviously want this to be a much lower resistance than the building. So therefore, the resistance of the lightning conductor is lower than the resistance of the building. Finally, it's almost impossible to test different designs of a lightning conductor in controlled experiments. Well, there's lots of answers to this one. One of them is that storms are unpredictable. It's a lightning storm. We can't predict where the lightning is going to go. So storms are unpredictable. And again, this leads up to many of the answers. For example, we can't predict the building. So we can't predict which building, the time. Yeah, exactly. We don't know when a storm will happen, and also you cannot create. So again, difficult to test. It's very hard to generate storm conditions. They require lots of energy to do this, and obviously a very large laboratory to test this to a reasonable scale, so it's very unlikely to happen. But again, any of these answers would be perfect. And that brings to the end this set of questions.